No, this is exactly the same as what we just saw, except that before I depicted C as an axis in one direction and N of AT, the null space of A transpose, as an axis in another direction. And that's not a very appropriate depiction unless you understand that those axes represent two orthogonal subspaces that could be of whatever dimension. In the case of the transformation we have here, C had dimension 3, so that axis actually represented a three-dimensional subspace, and the N of AT axis represented the other two dimensions, the subspace of the other two dimensions you need to get a direct sum for R5. Okay, so this representation isn't all that much better, although N of AT is a plane within R5, okay? The row space of A transpose, i.e. the column space of C, the set of vectors that you get when you map V into R5, okay, all of V goes into here in a one-to-one fashion, in fact. This is actually a three-dimensional subspace, so we can't really represent it by a rectangle. The plane is reasonably represented by a rectangle if we understand that the plane is actually infinite and the rectangle is just part of the plane. I could draw a three-dimensional subspace within here and a two-dimensional subspace, but how do I draw the fact that they're orthogonal to each other? How do I draw a three-dimensional subspace orthogonal to a two-dimensional subspace? I'd have to be able to draw a picture in R5, a picture in 5 dimensions. I've only got 2 dimensions on this board, and in 2 dimensions I can do some kind of a job of representing the third dimension because we live in a 3-dimensional space, or at least we perceive ourselves in a 3-dimensional space, and we can't visualize a 5-dimensional space. There's no way to visualize these subspaces, so this is as good a representation as we can make. I make them rectangles because they're orthogonal to one another, but I can't draw 2 rectangles that are perpendicular to one another. Yeah, actually I can, but I can't draw the 4-dimensional space that you would have from a direct sum of 2 planes, much less the 5-dimensional spaces that you'd get from a direct sum of a plane and a 3-dimensional space. Well, anyhow, that's just background. Just emphasizing the fact that this isn't an actual picture of what it looks like, it's a representation. The key thing we have to understand, in general, is that any vector in this space can be expressed uniquely as a sum of a vector in this space and a sum of a vector in this space. And that just comes back to the fact this is a direct sum, and we've pretty well established that whole idea. So I say that this is our vector B. Remember, B represents our set of y values when we're doing the depth model with whatever number of points. Okay, so here's our B. And I've represented a B sub rho for the B, for the vector in the row space that you need to add some vector in the null space to in order to get B. And then I've used B sub n for that vector in the null space, so that B is B rho plus Bn. And I say this is a unique, this exclamation point means that